Okay, I get to introduce in this video my absolute favorite law of physics. I know that sounds really geeky, but it really is. It's such a cool rule, and it's so applicable. It's not just magical in its concepts, but it's so applicable to our daily life. And this is Faraday's law. So I'm going to write it out in its full glory, and then we're going to break it down into its essential pieces. All right, so to start, Faraday's law is written in this very complicated way of an integral along a loop. That's what that circle means. It's a closed loop. So you start at one point in the loop and you go back to that point in the loop. And you're integrating, this is a line integral, we've seen this before, but we're integrating the electric field along the loop. Okay? And more particularly, we care about the electric field that's parallel to the loop. That's what the dot product says. Okay? And what Faraday's law says is that you can create an electric field along a loop if there is a changing magnetic flux, which, so we have a d by dt, that's the rate of change of a magnetic flux, which is a b dot dA. Okay. So we've talked about flux. This part right here is the magnetic flux. We've talked about what flux is, and you can see why we had to spend time on that, because this of itself is crazy complicated. But here, this is just another way of saying the potential along the loop, because if you remember, the electric field and potentials are related by distance. And so this is nothing else besides delta V induced, okay? And I could put induced here. This is the induced electric field, all right? And that is negative d by dt of the magnetic flux. So that looks a lot simpler, and remember, we have to keep these complex mathematical things clear physically. So this is just simply saying, what's the potential induced in a loop? Well, it depends on how the magnetic flux is changing as it goes through that loop. Okay, and we care about particularities. We care about how much magnetic field is going straight through the loop, and we care about the electric field that's along the circumference of that loop. Okay. Now, often it's current that we derive, and so very often that we can say, okay, the potential is going to be equal to V equals IR, and so we can say that that's IR. So this would be the induced current, where this would be the resistance in that loop. But what's important here, this is super important, is that this rule, these electric fields that are created are what drive that current, what create that potential. The field is more fundamental than the potential or the current that is driven. In fact, this can happen. You can get an electric field induced in space. There doesn't have to be a wire there. There doesn't have to be charges there. If you have a magnetic field is changing, then you draw a line in space, okay, through which that flux would change. You create electric fields in that space. And so that's what's super important about this, is that fields are what's fundamental. This is application. We put a metal wire in that space, and it'll create a potential on that wire, and current will flow in that wire. And so we can do something with it, which is also how we can measure magnetic fields. Okay. All right, now I'm going to break it down a little bit more. One is this minus sign. This is called Lenz's law. It's the simplest mathematical thing that has a name to it. Lenz's law is that minus sign. And basically what it says is that these electric fields respond in such a way as to try and oppose the change in the flux. That's what this is saying, is space or nature will create electric fields to cancel out any change, or to try and oppose any change that these magnetic fields cause. Okay? And that's called Lenz's law. Now that takes a lot of work to try and figure out, and so I'm going to do just some examples to help. So for example, let's say we have a loop of wire sitting in a horizontal plane. So I've kind of got it drawn, in and out. So that's a horizontal. We'll call this X, Y, and Z. All right? Now if I have a magnetic field that's in the Z direction, okay, so B equals BZ, all right? I've got this magnetic field that's pointing, so it's going perfectly perpendicular to this loop or parallel to the A vector, which is always perpendicular to this loop. Okay, so that field's going this way. Now, if the field's just steady, so it's not changing in time, well, this is all constant, and the change of a constant is 0. And so there's no electric field induced in this ring, or this space occupied by the ring, and therefore, since the ring's there, there's no potential difference, and there's no current flowing. But if I change this, there's a change, and there will be electric fields created to oppose that change. So let's suppose this is getting bigger. Okay? This B field's pointing up, so it's going up through this loop, and it's getting bigger. The electric fields will be created so as to cancel that out. Okay? They'll try and cancel that out. They're going to create a current, they'll create a field that would drive a current that would create its own induced magnetic field that opposes this one. So if you remember from our equation for the field of a loop is it points along the axis of the loop. So for example, this B field's pointing up. It's getting bigger, so the electric field will create a current flow in this loop so that the loop creates a magnetic field opposite that. Since it's getting bigger this way, it wants to create a magnetic field that's going down. Okay, so the induced field is down. So the applied field from something else is up. The induced field is down to cancel that because it's getting bigger. So what direction would current do to create that? Okay, so it's kind of hard to see with the angle here. But if I were to draw this from looking down the z-axis, so here's x, here's y, I want a B field induced that is into the page. So it's downward, which in this picture is into the page. So that's going to be into the page, so I'm going to see the crosshairs. All right, to create that means I need my thumb to point down, and so I need my thumb to point down with my right hand, my fingers curl open, and that makes a clockwise current. So this clockwise current will create, and that's the induced current. Okay, that induced current creates a B field, an induced B field, that goes down. So this applied B field, since it's up and getting bigger, the induced field needs to be down to oppose that getting bigger. All right, and so that's the direction the current would flow. Let's do a different one. Let's suppose that here's my ring again. Got the same axes here, x, y, and z. Let's suppose my B field is still up. This is the applied B field, but it's getting smaller. All right? If it's getting smaller, it's up, but getting smaller, well, the induced fields don't want that. They want to oppose it getting smaller. So instead of it getting smaller, they want to add to it. Say, don't get smaller. Let me add to it. So they try and add to it. So the induced B field is up. Okay. So if the induced B field's up, then if I draw my top-down view, okay, I want an upward induced B field, and that means my thumb's going to point up, and my fingers curl open, and I'm going to counterclockwise current. Okay? And we could have reversed this. I could have the B field going down. I could have the B field going down and getting bigger, going down and getting smaller. The main idea is that the electric fields will create a current to flow such that the induced magnetic field created by that induced current will oppose the change. So it's not as important as the direction the applied field points. It's whether or not it's getting bigger or smaller. Okay, so that is Lenz's law. Okay. Now the rest of it is just applying things we've done before. This side is just saying, well, potential is just electric field times length, and this side is just magnetic flux. So the whole crux of it is we care about change of that flux, no matter how it's changing. It could be changing because the area is changing. It could be changing because the B field is changing. But what we care about is the flux. Okay, in these cases, I chose to have just a changing B field. But we've seen in previous cases where the B field was constant, but the area changed. For example, loops being pulled out of a wire, or in like this case, we had a U-shaped conducting rail. We had a bar go across it, okay, and we pushed that way. Well, if there's B field everywhere, let's say pointing out everywhere in this region, well, here the area is getting smaller, so the flux of this B field is getting smaller and it's pointing out. Okay, so according to this rule, the flux is upward, pointing out at you, and getting smaller, so the induced current should be such to create a B field that is outward. It doesn't want it to get smaller. So B induced is out. Again, this flux is getting smaller because the area is getting smaller. The area within this loop is getting smaller as this rod gets closer to the other end. So B field's out, getting smaller, so the B induced stays in the same direction to try and keep it from getting smaller. Okay, well, what current would be created to create an outward B field? Well, my thumb's outward, my fingers open up this way, so I should get a current flowing this way, my induced current, which means across the bar, it would be that way. That would be I induced. Well, let's go back to our regular magnetic force law and see if that's consistent. Okay, so my charges are all sitting here. Here's my plus charges. They're moving that way, so I'm going to pull out my little doohickey. The charges are moving that way. Green is velocity. The applied B field is that one, okay, pointing out at you. That's this blue one right here. It's pointing out at you. And therefore, the force on the currents is to the right, which would drive current to the right, which we saw. So in this case, we could explain this with just the magnetic force law, old physics, things we've already done. In this case, nothing's moving. There's no QV cross B. There's no V. There's no charges are moving. But current is created here just because the magnetic field changes. So what we learn is that this law here, Faraday's law, is more fundamental. It describes why this worked. It's because of the flux, not just a changing area or moving charges. It's because this area changed. And that caused the electric fields created that were induced. Okay, so one last recap. This is pretty complicated stuff, but beautiful, beautiful physics here. Is that electric fields are induced, are created to respond to a changing magnetic flux. And they are created in such a way to oppose that change, in that they create a voltage that drives a current to create an induced B field to oppose the change. Okay? That's how it works. Changing B field induces an electric field that creates a potential, that creates an induced current, that creates an induced magnetic field that opposes the change.